So I'm going to talk today about deep reinforcement learning with subgoals. And this builds on lots of work that's been done by many great people over many years, too many to list. And also, in particular, I'm going to focus on three pieces of work. So thanks especially to Tom Charles, Radley, and Sasha Beshnevetska, the work I'm going to talk about. So I want to start by talking about unsupervised reinforcement learning. So what do I mean by that? Well, sometimes in RL we tend to just focus on this extrinsic reward, this sparse signal which the agent gets. Potentially, in life it may be at the end of a lifetime that you discover whether the agent's actually been successful or not in achieving its life's ambition. But agents live in this much richer world, this sensory motor stream with potentially thousands of observations streaming into it and these very rich and complex actions that it takes, potentially many times per second. And the key point is that these actions that the agent takes, these actions actually modify this stream, this sensory motor stream that it's going to see later on. So if I do one thing now, it's going to actually change the observations that I perceive later. If I turn my face one way, I see something different if I turn it to the other way. And so we can think of the goal of an agent as rather than just being to actually maximize its reward, we can give it a new goal, which is actually to be able to control its own future, to surf this stream of observations and actions, to be able to modify them, to modify this sensory motor stream, to try and achieve the goals that it wants to achieve, to try and control its own future. And so, if an agent really can control this stream, if it really can control what as much as it's possible to control the observations that it's going to see, that means it really can actually change its future in a way that means it will be able to maximize any reward signal that we choose to give it. So really, in some sense, the overall objective of our agent should not just be to maximize for one reward, but for all these possible things which could happen to it. And if our agent can manipulate any of those, it has as much power as we can want. So of course the future is a very big place, and we have to pick out particular salient aspects that we want to control. And so in this talk I'm going to use the term subgoal, which really means focusing on controlling one particular aspect of the future. So examples of subgoals might be to minimize the level of hunger that the agent is experiencing, or thirst, or maximizing energy, or minimizing the distance to my house. But I think really one of the points I want to bring home is that these subgoals don't necessarily need to be particularly complicated. That even if you specify a very simple subgoal, such as making one pixel on my retina red, that actually to optimally achieve the optimal behavior for that particular subgoal requires immense capabilities. So for example, to make that pixel red, I might need to master manipulation to be able to pick up a red object and place it in front of my eye. I might need to be able to master locomotion so I can walk over to a red object. Or I might need to master communication to actually get someone in the audience to throw me a red ball. So just for that very simple subgoal, to master that subgoal requires immense capabilities. So then we have two questions which we're left with, which is how can we find these subgoals? Right? How can we find relevant things in the environment to try and optimize for? Well, we already have those capabilities. That's what deep learning gives us. Deep learning has the ability to find features which are salient aspects of the environment. And we also already have the capabilities to optimize for those subgoals, to know how to achieve those subgoals. That's what reinforcement learning gives us. Reinforcement learning gives us the ability to control for these subgoals. It gives us the ability to supply any subgoal we want, and RL tells us how to maximize for that subgoal. We just convert it into some kind of reward description, and our RL algorithms already know how to find the optimal policy, the optimal behavior for achieving that goal. So one way to think of this is that subgoals give us divide and conquer for reinforcement learning. Real-world RL problems are really hard. There's all kinds of immense complexity inherent in the problem of solving some very challenging RL problem, particularly when you start to get long horizons involved in these problems. So the idea of subgoals is that they first of all divide the hard problem, which might involve sparse long-term rewards of realizing your life ambition, with some easier subgoal, like just maybe move from one room to another. And then once those easier subproblems have been solved, then we can start to put them back together, put back the pieces that we've actually discovered from solving those easier problems into a larger overall solution to a much more challenging problem. So the pieces that we put back together might take different forms, but for example, they might be the policies, the behavior that actually helped the agent to get out of the room might then be useful to help it to achieve its life ambition later. Similarly, the value function that was discovered for solving this problem might be, these value functions might be composed together to give you some richer behavior. And finally, the representation that was discovered by solving this easier problem, the features which were useful to solve that easier problem, might also be very helpful for solving the harder problem. So divide and conquer is really key here. We don't just want to focus on the overall problem immediately, we need ways to make our hard problem easier, such that then when the real rewards come along, we already know how to deal with it. We've already understood the world and can do all kinds of things. So I'm going to make that a little bit more concrete now. So what do we mean by a subgoal? Well, let's define a subgoal. So it's going to be defined by two things. A pseudo-reward function, which basically just says how good is it to be in any particular state if you're trying to achieve a subgoal. So if I'm trying to leave this room, it might be that my subgoal is +1 if I'm outside the room and 0 if I'm inside this room. And the termination condition just tells us the temporal scale over which we care about optimizing this. So again, we might just have a temporal condition, which is if I actually leave the room, then this will terminate. Now subgoals can actually be parameterized to give us a whole vector space of possible subgoals. And that's what we're going to look at in this talk, is how to parameterize it into some vector space. So for example, if we think about trying to reach a particular location, we can now parameterize that location by some coordinates describing where it is. And so now we can have a pseudo-reward function that tells me how happy I am, how much progress, how happy I am with how far I've got towards any particular location, and a termination condition which says, and for each of these locations I might be trying to get to, am I done? Am I done with that particular task that I've been assigned? So you can just think of this G as like a vector encoding the task that we care about. And we're going to allow ourselves to, instead of just having one task we care about, we're going to allow ourselves to have a vector input that tells us which of those tasks we're actually trying to solve for at any given time. So the subgoal in itself doesn't give us any behavior, it doesn't give us a value, it doesn't give us actually the optimal behavior. It just tells us like the scaffolding. It gives us the goal, it tells us what the objective is. To actually get to those behaviors, we need to have other quantities, the usual ones that we use in reinforcement learning. We need value functions and policies. In particular, we're going to have a subgoal value function, which basically tells us how much reward we're going to get. Like if I'm in a particular state and I'm trying to get to a particular goal, how much reward am I going to get? So you can think of this as some agent that's trying to get from one place to another place, and this subgoal value function just tells you how far this agent is away from that goal. That's an intuitive way to think of it, as the distance from the state to the goal. Now the subgoal optimal value function tells us not just how much it expects to get, how much reward it expects to get, but what's the optimal value function? Really, how far away is it if it was to choose the optimal path from one place to another? And similarly, we can have the subgoal optimal policy, which tells us the way to actually, the actions that it should take. If it's trying to get from here to here, what action should it take next? And so these are really just the natural extensions of our normal RL concepts, but to allow us to take any input describing the task. So we can generalize over a much wider space of possible tasks from just one. And that leads us to the idea of the universal value function approximation. We call this the UFA. The key idea is that one deep neural network can represent knowledge about all subgoals. So we call this the UFA, and it's basically a function approximator for this whole space of possible tasks. So you can think of this as a really powerful form of knowledge, like telling us how to control a really wide array of different tasks within this stream of sensory motor control. There's two ways this could be represented. It could take this, both the state and the subgoal as an input, and now you've got some big function approximator like your deep neural network, and it outputs a value function. So again, you can think of this as the input saying I'm trying to get from here, and I'm trying to get to here, and it tells you as an output how far away you are. But we now have this for a whole space of possible states, a whole space of possible goals. And similarly, we can do this with subgoal out. We can have a state that comes in, we can have n different tasks enumerated, like I'd like to be able to get to either this location or this location, like the room to the left or the room to the right. And this tells you in one shot a value function for all of those different goals which you've specified. We can do the same thing with a policy. You can have a universal policy which again takes the subgoal in as a description and tells you which action you should take if you're trying to achieve that task. I'm not going to dwell on that. Now one thing to note is that these quantities, these UFAs, can be trained off policy. So one of the nice things is that all of this knowledge that we need to know about, you don't have to follow behavior specifically. You can follow any arbitrary behavior and yet still learn about all of these possible things that you could do. You can learn about what would the optimal value be of trying to get over here, whilst you were actually trying to do something maybe related but not the same. And that really means that we can learn much more efficiently by learning about many different things that the agent could be doing whilst following one stream of experience. just going to give a couple of illustrations. So here's the first one. It comes from the kind of classic toy domain, 4 rooms example. And there's an agent here that's just specified the goal of trying to get to some location in this little grid world. And what we see here is a UFA that's been trained to reach all possible goals in the top left room, the top right room, and the bottom left room. But it's never been trained on how to get to the bottom right room. And here what we're saying is what happens when we ask it now, without any further training, so this is zero-shot generalization, we're asking it to try and get to the red spot, despite never having seen these examples during training. You see, it doesn't do a perfect job. You can compare this to the ground truth, but nevertheless, even without saying anything, it's able to generalize because it's seen related experience, and it's able to generalize from that experience to actually other tasks to which it might be assigned. We could do the same thing in a slightly richer example. So this is the Atari game Miss Pac-Man, and at the top here we see that we assign a UFA to train on how to get to certain locations on this in Pac-Man. We gave it the task of trying to pick up these different pills here that are marked in green on the top left there. And then we tested it on a completely different set of pills to see if it then knew how to reach all of these other pills. And then we tested and we compared this kind of, we don't have the ground truth here, but we could actually train a specialized agent for each one of these tasks separately. And that's what we see as the truth there. And then at the bottom we see what a UFA trained to learn about all of these things was able to do. And you see that it really captured the value function quite accurately relative to this truth which we've learned about. So these are just examples where you have a whole space of possible goals which an agent's been asked to understand. It's been asked to understand all kinds of different tasks which it could be trying to achieve in its environment. And it's got one underlying representation, this UFA, which has been trained to achieve all of them. So I want to change gear a little bit and talk about subgoals in a bit more detail now, about what they are, what the geometry is of these subgoals, and how we should choose them. So the first question is, how should we select which subgoals we should actually learn about? So as we've seen, we have the ability with off-policy learning to learn about any subgoal we want. So which one should we learn about? Well, here's just 3 ideas. I'm sure there's more. The first idea is to do it coordinate-wise. In other words, we have one subgoal for each state dimension. And so for each dimension in your state space, for example, this could be in the input space, it might be that you learn to control each pixel separately. Or in your feature space, you might learn to control each feature separately. And an example of that would be the Unreal architecture I'll talk about shortly. Another idea would be to use your hindsight to try and, if you've already reached a state in the past, how do you get back to that same state again? And that's the idea of hindsight. So, for example, OpenAI had a paper at this conference on hindsight experience replay, which uses this idea. And the third idea, which I hope to come to if I have time, is feudal reinforcement learning, which is an old idea from Peter Dyan and Jeff Hinton. And the idea there is to treat subgoals as actions, to actually make the choice of subgoal part of the reinforcement learning problem. So you have some high-level agent that chooses the subgoals which are most effective for achieving its overall aims. And so an example of that would be the fun architecture. So we've described this idea that we can actually underlie the space of possible subgoals by parameterizing by some vector describing what kind of task we want to achieve. And so what's the nature of that subgoal vector space? Well, there's 2 possible examples which we can talk about here. The first of which we call pixel control. And this is where the vector space representing subgoals is represented directly in the raw input space. So we call it pixel control because this is typically done in visual domains. But it could be done in any input space. So in a visual domain, this would be that each element, each subgoal specifies a separate pixel. We have a separate goal of making this pixel red or making this pixel change as much as possible. And you have a whole array of these different tasks, which can be represented very efficiently and use the magic of convolutional networks to actually understand all of these different tasks at once. The second idea is feature control, which is to say, instead of representing these pixels in the concrete input space, let's abstract them. Let's actually have abstract subgoals. For example, something like, if you have a feature that your network has learned, which represents something like hunger, well, let's have a subgoal of actually maximizing that feature, to kind of minimize that feature, to make you to sate your hunger, or to sate your thirst, or maybe minerals and gas in StarCraft would be another example. And these features are trained in the usual way. So they can be trained by back-propagating this universal value function approximator back into features. So whatever features you're actually discovering and learning about whilst you're building up this knowledge become the features in the next generation of your algorithm that you actually choose as targets as your next set of subgoals. Or you can backpropagate some other losses and use those to drive your features. But the key idea is that the deep learning actually builds up these features and enables you to learn about them. And here at the bottom we see that we can represent this by some vector space with like hunger and thirst as two different dimensions. And now, when we specify a goal, we can either specify this coordinate-wise by just picking either hunger or thirst, or we can specify some point in this space by saying I really want to achieve 0.8 hunger and 0.6 thirst. So the Unreal architecture is actually a little bit more complicated than what I'm going to describe. I'm going to focus on what I consider to be the key element of the Unreal architecture. So this is unsupervised reinforcement learning with auxiliary tasks. And for a while it's been the top performing agent at DeepMind, particularly on tasks like the DeepMind Lab, these three-dimensional control tasks. And so what we see here is that there's a recurrent network that's representing state. It's taking in all of these pixels and building some representation of state as it goes along. And it outputs three quantities. The first two quantities are exactly the same quantities that get output by the A3C algorithm. So we've got this policy which actually picks what the agent's actually going to do in reality. So this is for its real task of maximizing reward. It's got a value function for the real task as well. This is also just the usual A3C thing. But it also has this subgoal out UFA that's trying to basically do coordinate-wise predictions of pixel control or feature control. So there's all of these different Q outputs here, and each one of them is basically saying what's the value function for this particular pixel here, or this particular pixel here, or for this feature in my network, or this feature in my network. So it's simultaneously learning how to optimize for potentially thousands of different subgoals at the same time. And this gives it a very, very rich representation. It means that it can build up this state representation vastly more efficiently than if it was just focusing on the sparse reward signals that you receive at the end of this task. So how well does this actually do in practice? Well, this plot shows a whole bunch of different components of the A3C algorithm, but I just want to focus on the black line at the bottom, which is the raw A3C line, and the yellow line, the second one from the top there, which is what happens when you take A3C and you just add in this pixel control element. So if you just add in these Qs, in addition to what you had before, you add in this third arrow here to represent the value functions for all of these other tasks. And you get this enormous jump, which is, gives you something like an order of magnitude improvement in the efficiency of learning in these tasks, these three-dimensional navigation tasks. We can also do the same idea with feature control. So instead of optimizing for the pixels, we now optimize for the features in the agent's own network. So this is really nice. It shows that this idea is actually stable and works. In these particular tasks, it turns out that pixel control is particularly effective, but it's nice to know that if you're in some other kind of task where pixels aren't necessarily the right thing to do, that we have an automatic procedure for picking out the right abstractions, just using feature learning, and by learning to control the features in the agent's own network, like it's learning how to maximize its own hidden rate, its own hidden state, it's learning how to control its own hidden state representation. So in some sense, this is really getting back to that idea of being able to control its stream, control its own stream of the future. It can control its own hidden state, that's what the green line is. And it's both of them give an enormous boost above the raw A3C, and you see that this is quite a robust and successful idea. And I also just wanted to highlight this particular plot, which is this is what shows, what we see here is how important it is to actually understand how to control the future and not just predict it. So what we compared to here was the same idea of pixel control, but instead of actually trying to control that pixel, instead of like learning how do I make this pixel here red, we learned to predict whether it was going to be red at the next frame, or we learned to predict whether it was going to be red over the same time horizon we used for pixel control. And we see that in all of those cases it does much, much worse. It's really important to learn how to control something. If you just learn to predict whether I'm going to see red, that doesn't force me to learn about locomotion and communication and all of those other things. The prediction of whether I'm going to see red is much more boring in some sense. Okay. How much time do I have? Can I just get a time check? Okay. So I'm going to just talk briefly about some other ideas. I really want to focus on what's the nature of subgoals? Like, what does it really mean to have good subgoals? How can we understand this vector space describing subgoals? So the first idea I want to bring in is this idea of abstraction. And this is a really old idea that's been used in classical planning for decades, and has been one of the key ideas that's enabled planning methods to be super successful. And the idea is that you're able to ignore, to say, I don't care about some dimensions. I just don't care about, right now I really care about hunger, but I don't care at all about whether I'm thirsty. And that ability to ignore things gives you an enormous improvement in performance. So for example, in these classical planning domains, when you try to solve these sliding tile puzzles where you have to order the pieces of the sliding tile puzzle, the most effective methods to planning are all based on this idea of abstraction, where they learn to ignore the location of some of the tiles and just optimize for the rest of them. And that idea is the way that divide and conquer is being achieved in planning, and it's been super successful. In addition, we want the ability to have these very rich behaviors where we can coordinate many different subgoals at the same time. I don't just want to be able to monolithically say, I want my agent to be focusing on getting out of the room. I want it to be able to understand a whole host of different things simultaneously. So for example, right now, I'm simultaneously standing upright and I'm talking to you guys and doing all of these things, and I'm also scratching this little itch on the back of my head, all at the same time. And those are all different kind of sub-goals which are being balanced and combined together. And so you can think of this, like Rich Sutton calls this the sub-goal keyboard, that you want to be able to play a whole chord of different ideas and specify all of these different tasks at the same time. So how can we achieve these ideas within our vector space, within this representation that we have in like either pixel control or feature control? Well, we can specify a geometry to our sub-goals by choosing either something like a target geometry or a direction geometry. A target geometry says, well, my sub-goal is going to be to reach a particular target state, like I want to reach particularly 0.8 thirst and 0.6 hunger. Whereas direction says I'm just going to specify a direction in this vector space of sub-goals, and then I want to maximize my progress in that given direction. So just to make that a little bit more concrete, if we were to use target sub-goals, you could imagine specifying some particular location in your vector space G there, and you might be in some state S. And so now you can say, well, how well am I doing? Well, you could think that there's some epsilon ball around that which maybe determines whether you've achieved your goal or not, and how well you're doing can just be determined by your distance to that goal, the distance between S and G. And progress towards that distance might determine the amount of pseudo reward that you're given. So that would be the idea of specifying a target. You're just trying to get closer and closer and closer in this vector space towards some specified goal. But there's an alternative to that. Well, let's first of all point out the weakness of this approach is that you don't have abstraction. We get this idea of coordinated goals. We can say, well, I want to achieve a certain amount of thirst and a certain amount of hunger at the same time, but we lose the idea of abstraction. Although you could make elliptical things, but then it gets rather complicated. So an alternative is to use direction subgoals. And so here, this visualization, again, this is in the same kind of vector space where you care about hunger and you care about thirst, but now we can say that the pseudo reward here is given by progress in a particular direction. So we're specifying this G and saying, I really want to just see how far I can get in that particular direction. I really want to be as dry as possible, or I really want to maximize some hidden feature to its maximum extreme value. And I just want to give pseudo rewards out without limit based on how well the agent does in achieving that task. And that can be done by just projecting the agent's state onto that direction, or by measuring the cosine similarity, basically the angle between where the agent's actually moving in state space and where we would like it to move in this state space. And the nice thing about these is they give us this abstraction idea. It gives us the ability to ignore particular dimensions. So you can ignore a dimension just by zeroing out one of these dimensions, by saying, I'm going to assign 0 hunger in my goal direction. And that means we now have the ability to completely ignore that when we actually compute this. So you can do the sliding tile puzzle kind of idea, where you can ignore certain dimensions and just measure progress along the directions that you do care about. So it gives you this very powerful idea that you can really say, well, I don't have to specify precisely in all its complexity the part of the world I want to reach. I can say I just care about particular aspects of the world, and these are the aspects of the world I really want to maximize. Okay, so I'm just going to change gear one final time here to talk about temporal abstraction, and then I can try and bring it all together. So the idea of temporal abstraction is to say that we really want to be able to build these high-level actions. So if you think about the options framework from Rich Sutton and others, the idea is to say that you want to have some action which is temporally abstract. We don't need to or want to reason about the world at a millisecond level if you're controlling a robot. We want to reason about it at this much higher level of leaving the room and recharging itself from the power charger. And so the way we can do that with these subgoals is that subgoals actually induce options. So if you know how to achieve a subgoal, once you've figured out how to achieve that subgoal, you immediately have an option because you already have the policy that gets you there. So if you've figured out, if you've done your RL to try and, like we did in Unreal, if you've actually figured out how to get to this particular thing, and you know how to achieve, you know how to get out of the room, or you know how to minimize your hunger or your thirst, or whatever it is, you immediately have an option because you have the behavior that tells you how to get there, and we also know when to stop because that was part of the definition of the sub-goal. So those are the main components of an option. We have this temporal abstraction. We have a higher level action which we can now use in our agents to actually do something more abstract. So this brings us back to the idea of feudal reinforcement learning, the sub-goals as actions idea. And so I really want to think of this as a framework for hierarchical reinforcement learning, to say that at every level of our agent, we have this fundamental idea that we've got some hierarchy, and into that hierarchy we've got some, like this box here, which basically says, you can think of each part of this as an agent, and maybe a high level, a mid level, a low level, whatever it is, but each of these agents is trying to achieve some super goal, capital G here. And how does it achieve that super goal? Well, it achieves that super goal by picking some sub-goal for its lower level agent to go and achieve. So you can think of this as like the general, asking the lieutenant to go and do something, the lieutenant goes and asks the soldiers to go and do something, and so forth. And at the end of the day, some actual action gets picked, which achieves some high level reward. So the highest level gets fed the actual reward for the problem, and the lowest level actually picks actions. But now we have a real approach to hierarchical RL, and the whole thing is RL all the way up. It's sub-goals as actions. This decision of which small g to take is a reinforcement learning action. It's a decision that gets taken by the agent using our usual RL mechanisms. So each module of hierarchy we can actually think of as an RL agent. So, and what does this really mean? Well, when we pick a G, we really need to understand, what does it mean to actually pick one of these little G's? Well, you can't measure how good a sub-goal is, you can only measure how good it's effective. You need to know, how good is the actual option that really takes me out of this room? Because until you've experienced that option, you don't really know how effective it is. Okay, so I'm going to talk briefly now about fun. So this is a deep reinforcement learning architecture for feudal reinforcement learning. Using these direction sub-goals, using these specification of a particular direction. So what happens is in fun, there's two-level hierarchy. There's a manager and there's a worker. And the manager selects some kind of direction sub-goal. And it chooses, so which direction does it choose? Well, it uses this idea that it's going to pick this sub-goal direction that maximizes reward. So this is the feudal idea. The sub-goal is picked. We pick this direction as an action. So it's the sub-goals as actions idea. It's really picking the sub-goal direction that enables it to achieve its overall reward as effectively as possible. And once it's specified this sub-goal, it's specified some direction it wants to achieve in this abstract space. So it's like specified, I really want you to sate your hunger right now. The worker goes off and tries to do that. So it selects actions that actually then maximize the cosine similarity to that angle. So it tries to find a path through state space that actually has an angle that's as close as possible to this path that's been specified by the manager. So the manager said, go in the direction that kind of decreases your hunger, and if you find yourself going in a direction that kind of decreases your hunger but also decreases your thirst a little bit, well, that will have a certain alignment in this state space to what you've asked it to do. And of course, to be able to do this, underlying all this, we need some general representation that can tell you how good any one of these goals will be. Like, how good is it to take any one of these directions? How well am I doing? How can we need to know, if I specify this direction of satisfying hunger or satisfying thirst, how well is the worker currently doing at it? Or equivalently, so that would be the UFA. Or equivalently, we could have a policy that says, if I specify this particular direction, which action should I take? So we need that knowledge. We need the ability to now be able to specify any possible direction, and the worker will be able to know how to do it. So the worker needs to have this powerful form of knowledge underlying it. And in this case, we use a sub-goal in UFA. So in other words, there's a big neural network which takes as an input both the state and the direction that's been asked to take, and it can output both the value and an action to take in that situation. If I've been asked to maximize thirst, what should I do? And there's a big neural network that's trained to satisfy that by RL. So what we see down here is that if you apply this to something like the game of Montezuma's Revenge, this idea really helps. Like having these temporal abstractions in there really helps. It kind of learns to pick out sub-goals and then follow those sub-goals. So just the plot on the left shows that it gets a lot more score. It gets through several of the rooms in Montezuma's Revenge. And on the right, what we see is that actually this is a visualization of the subgoals that it's actually picking out in Montezuma's revenge. So we see what this is basically showing is in the duration of one episode, which subgoal was most popular. So at the end, we have to look at which subgoals were most popular, and the ones which are actually picked out are these big spikes here. And those spikes tell us, basically go back in time and say which of these states that it visited is closest to which of the states that it actually visited ended up being selected as the subgoal by the agent more frequently than any others. And what we see is that it's ended up picking out these big spikes represent the moment where it gets past the kind of monster at the bottom and the moment where it picks up the key at the left-hand side. And it's really understood that these are kind of the key subgoals which it should pick out for itself. But the whole thing has just been trained by this kind of feudal end-to-end reinforcement learning process. I just wanted to show one last demo and then I'll be done. So this is what happened when we applied fun to, this is called the Morris water maze. It's a kind of fun problem where we have an agent which is dropped down into a maze. This is something which is done to real rats, by the way. And it's dropped into this water maze. And it's a partially observed problem. And there's this platform hidden somewhere in this maze. It doesn't know where the platform is, but it wants to be on the platform because if the rat is on the platform, it's dry and it hates being wet. And so it kind of swims around and around. It can't see this platform. It doesn't know where it is until it discovers it. And then it's immediately put down somewhere else in this water maze and has to find its way back to the platform as quickly as possible. And what we see is that when we run fun on this task, it actually has this ability to be able to navigate around here. And what we see is that these different colors basically represent the moment where it switches its subgoal. So it's actually found subgoals where not only does it, so we see these color trajectories are showing that it goes to the goal, and then immediately afterwards it's able to reset back to the goal on the next trajectories. So after it explores around the first time, like these blue and red and kind of brown trajectories show that it then immediately goes back there once it's reset. And this right-hand one shows that these are actually the kind of the different subgoals that it's picking out correspond to these different exploration strategies, like this red and this blue and this yellow, kind of corresponding to different subgoals that it's figured out for itself. Do I have time just to show a video? I'll just show a video quickly, and then I'll be done. I think it's fun to show a video. So first of all, this is the Unreal architecture that I talked about earlier, and then I'll show the fun one in a minute. So this is Unreal, learning to navigate through a maze. So this is the agent that's basically been trained with all of these auxiliary tasks to do pixel control. So it's learned how to control all of these different pixel patches, and it's learned to solve all of these different tasks. And I'll just quickly skip through some of these. And what we see is that when we start to visualize what it's doing, it's learned to control, we'll see on this right-hand side in a minute, it's got this visualization where we can see that it's learned to control all of these different patches of the screen. These kind of black and white patches show how much it predicts those different pixels are going to change. And it's got this understanding of which parts of the screen are likely to change and which ones are static. And the final video is for this feudal reinforcement learning. And here we actually see this rat going round and round and trying to find this platform in the water maze. So at the moment it has no idea, it can't see it until it lands on it. So it really just has to discover it. I've got the right video there. Oh yeah, there it discovers it. And then it gets reset and it has to be able to find its way back there immediately. Okay, so I'm basically done. I just wanted to finish by saying that, if you really have any takeaways from this talk, it's these ones. It's that subgoals give us the ability to divide and conquer RL. And that UFAs give us this powerful form of knowledge that enables us to control the stream. The agent can control and surf this whole stream of its future. There's a geometry to subgoals, and in particular, if you specify these directional subgoals, it gives us both abstraction and coordination. And finally, feudal reinforcement learning gives us the ability to pick subgoals as actions. It gives us the ability to bring this choice of subgoals back into the reinforcement learning framework. Thank you very much. I probably used up all my time for questions.
Well, we could have one good question.
Anyways, the Unreal architecture, you never said how, so you learned the pixel control, but how do you actually use that in the actual policy when the agents are executing?
Okay, so the question was, I didn't specify how the agent in Unreal used the knowledge that it found by actually when it trained all these other tasks. And this is a really good point. I should have made this much, much clearer, which is the whole idea of Unreal is that these tasks just hang off it. They do nothing. We do nothing with them. They just hang off there as additional auxiliary tasks. And the amazing thing is that by doing that, we force our agent to learn features which are effective for the tasks we really care about. So what's being reused is actually the representation, because you can see that these all hang off the same neural network. And so that neural network is being forced to share amongst all of these auxiliary tasks and the task we really care about, of solving reward. So the divide and conquer here is that we're solving these easy tasks. That forces it to learn features which are then immediately available and useful for the task that we care about. Thank you.
Okay, let's thank the speaker one more time.